Have you ever wondered what happens when old-school mechanical knowledge goes head-to-head with modern computer-controlled precision? What if I told you that in the late 1990s and early 2000s, immigrant mechanics armed with nothing but wrenches, timing lights, and decades of experience were consistently beating factory-tuned cars worth 10 times more? This is the untold story of how forgotten mechanical arts became the secret weapon in America's underground racing scene. And picture this. It's 2001, and on an abandoned industrial road outside Los Angeles, a bone-stock-looking 1992 Honda Civic with 180,000 miles on the odometer lines up against a brand-new BMW M3. The BMW cost $56,000. The Civic, maybe $2,500 on a good day. The BMW's owner smirks as he revs his 333-horsepower inline-six. The Civic's engine sounds like a sewing machine with respiratory issues. But when the flag drops, something impossible happens. The Civic launches like it's been shot from a cannon, pulling 2 car lengths before the BMW driver even processes what's happening. By the quarter-mile mark, that raggedy Civic is 3 car lengths ahead, having just run a 12.8-second pass to the BMW's 13.4 Outsmarted. The bewildered BMW owner demands to see under the hood. What he finds defies everything he thought he knew about modern performance. No aftermarket computer, no expensive engine management system, no nitrous. Just an engine bay so clean you could eat off it, with every bolt safety wired like an aircraft, every vacuum line replaced with silicone, and timing marks painted on the crank pulley in what looks like nail polish. The man responsible? A 58-year-old mechanic named Miguel Santos, who learned his trade in the 1960s, fixing agricultural equipment in rural Mexico, and hadn't touched a computer diagnostic tool in his life. And this wasn't a fluke. This was happening all over America. Immigrant mechanics from Mexico, Guatemala, Honduras, the Dominican Republic, and Puerto Rico were taking cars that dealerships had given up on and turning them into giant killers using techniques that weren't taught in any modern technical school. They were the keepers of mechanical knowledge that the industry had abandoned in favor of computer diagnostics and bolt-on parts. And they were proving that sometimes the old ways weren't just different, they were better. To understand how this underground revolution happened, we need to travel back to the 1960s and 70s when these mechanics learned their trade. In countries where replacement parts were scarce and diagnostic computers didn't exist, mechanics had to actually understand how engines worked at a fundamental level. They learned to diagnose problems by sound, smell, and feel. A slight variation in exhaust note could tell them which cylinder was misfiring. The color of spark plug deposits revealed fuel mixture problems down to the individual cylinder. The way an engine stumbled under load indicated whether the issue was fuel, spark, or compression. And then these weren't shade tree mechanics guessing their way through repairs. They were craftsmen who understood thermodynamics, fluid dynamics, and mechanical harmonics at an intuitive level. In rural Mexico, if your tractor broke during harvest season and the nearest parts dealer was 300 miles away, you didn't have the luxury of ordering a new component. You had to understand why it broke and figure out how to make it work with what you had. Once Miguel Santos learned his trade in exactly these conditions. His father was the only mechanic in a farming community of 2,000 people. By age 12, Miguel could rebuild a carburetor blindfolded. By 16, he was porting cylinder heads with hand files, understanding that smoothing the intake ports increased airflow velocity, which improved cylinder filling, which made more power. He didn't learn this from YouTube or a forum. He learned it from watching his father and from thousands of hours of trial and error. And not and then when Miguel immigrated to Los Angeles in 1987, he brought this knowledge with him. He found work at a small garage in East LA, mostly fixing the cars of other immigrants who couldn't afford dealership prices. But he noticed something interesting. The modern fuel-injected cars everyone was driving had abandoned many of the optimization techniques he'd grown up with. Manufacturers had gotten lazy, relying on computer controls to compensate for mechanical inefficiencies. The problem setup was perfect. By the late 1990s, the import tuner scene was exploding. Young enthusiasts were buying Honda Civics, Acura Integras, and Mitsubishi Eclipses, trying to make them faster. The conventional approach was to bolt on aftermarket parts, cold air intakes, headers, exhaust systems, and especially programmable engine management systems. Companies like AEM, Honda, and Apexi were making millions selling plug-and-play solutions that promised easy horsepower. But here's where it gets interesting. While everyone was focused on adding parts, mechanics like Miguel were focused on optimization. They understood something fundamental that the bolt-on crowd missed. An engine is an air pump, and its efficiency depends on how well air flows through it. You could bolt on all the parts you wanted, but if the foundation wasn't optimized, you were building on sand. Let me explain what Miguel would do to a typical Honda B16A engine, the 1.6-liter VTEC four-cylinder that powered countless Civics and Del Sols. First, he'd completely disassemble it, not just the head, but everything. Every component would be cleaned, measured, and cataloged. He'd check the deck height of the block with a precision straight edge. Even a variation of 0.02 inches could affect compression ratios between cylinders, causing power imbalances. And next came the cylinder head. This is where the magic happened. Honda's factory casting process left rough surfaces in the ports. These irregularities created turbulence that disrupted airflow. Using nothing but hand files, sandpaper, and decades of experience, Miguel would spend 20 hours reshaping each port. He wasn't making them bigger, that was amateur hour. He was making them smoother and reshaping the short side radius of the intake ports to maintain velocity while reducing turbulence. And the valve job was even more critical. Factory valve seats had 3 angles, 30 degrees, 45 degrees, and 60 degrees. Miguel would cut 5 angles, sometimes 7, each one precisely calculated to smooth the transition of air around the valve. He'd narrow the valve seats from the factory 0.60 inches to 0.040 inches, reducing the contact area and improving heat transfer. Then he'd back-cut the valves themselves, removing material from the backside to reduce weight and improve flow. But here's where his old-school knowledge really shone. The combustion chambers in mass-produced heads varied in volume by as much as 2 cc between cylinders. This meant compression ratios weren't equal, causing some cylinders to make more power than others. Miguel would carefully grind each combustion chamber to exactly 42.5 cc, ensuring perfectly matched compression ratios. He'd polish the chambers to a mirror finish, not for looks, but because smooth surfaces reduced hot spots that could cause detonation. And as the bottom end got equal attention. Factory pistons had casting marks and rough surfaces. Miguel would smooth every surface, knife-edge the rod beams to reduce windage, and balance the entire rotating assembly to within half a gram. He understood that at 8,000 RPM, even tiny imbalances created harmonics that robbed power and shortened engine life. Then came the truly forgotten arts. Port matching, where the intake manifold runners were perfectly aligned with the cylinder head ports. Thermal barrier coatings applied by hand to piston crowns and combustion chambers, keeping heat in the combustion process instead of letting it soak into the metal. Exhaust ports, ceramic coated to maintain gas velocity, every modification based on fundamental physics, not marketing claims. Dunch-wunch-wunch-was, the technical deep dive, reveals why this approach was so effective. A stock Honda B16A made about 160 horsepower at the crank. After bolt-on modifications, intake, header, exhaust, and a chip tune, most enthusiasts saw maybe 175 horsepower. But Miguel's engines, with the same bolt-on parts but proper foundation work, would make 195 to 200 horsepower. That's a 15% advantage from optimization alone. Lieutenants, the reason was volumetric efficiency. A stock B16A achieved about 85% volumetric efficiency at peak torque, meaning it only filled its cylinders to 85% of their theoretical capacity. Miguel's careful port work, valve job, and optimization pushed this to 95% or higher. At 8,000 RPM, that difference meant each cylinder was ingesting 10% more air per cycle. More air meant more fuel could be burned, which meant more power. Nay, but raw power was only part of the story. Miguel's engines had perfectly linear power delivery, no flat spots, no sudden VTEC kick that unsettled the chassis. The power came on progressively and predictably, allowing drivers to maintain momentum through corners and optimize their launch technique. The balanced rotating assembly meant the engine could rev faster and more smoothly, reaching its 8,500 RPM redline without the vibration that plagued hastily built motors. And on the fuel system optimization was another forgotten art. While everyone was installing larger fuel injectors and adjustable fuel pressure regulators, Miguel was blueprinting the stock components. He'd flow test each injector and match them within 1%. He'd modify the fuel rail to eliminate pressure drops. He'd index the injectors so their spray patterns were optimized for each port's airflow characteristics. The result was perfect cylinder-to-cylinder fuel distribution, something even expensive aftermarket systems struggled to achieve. Ignition timing was where old-school knowledge really trumped modern solutions. Programmable ECUs allowed infinite adjustment, but most tuners just followed base maps they'd downloaded online. Miguel used a timing light and his ears. He'd advance timing for each cylinder individually, finding the exact point where power peaked without detonation. He understood that cylinder number 4, being farthest from the water pump, ran slightly hotter and needed 2 degrees less advance. He knew that under certain atmospheric conditions, timing needed to be adjusted by half a degree. A note at the transmission received similar attention. Synchronizers were polished and clearanced. Gear sets were rem polished to reduce friction. Shift forks were lightened and strengthened. The result was a transmission that shifted faster than any short shifter kit could achieve, with perfect rev matching, because the reduced rotating mass allowed faster speed changes. But the real secret weapon was suspension setup. While everyone was slamming their cars on coilovers and calling it good, Miguel understood weight transfer, suspension frequency, and damping ratios. He'd spend hours corner-weighting cars on bathroom scales, adjusting spring perches a quarter turn at a time until the cross weights were perfect. He'd modify bump stops to prevent suspension bottom out. He'd clock the springs so they compressed in perfect alignment. Then, in the tire pressure optimization alone was worth half a second on a quarter-mile pass. Miguel didn't just check pressure when tires were cold. He understood that tire pressure increased with temperature and that optimal launch pressure was different from optimal top-end pressure. He'd start with 28 psi in the drive wheels, knowing they'd heat up to 32 psi after a burnout, providing the perfect contact patch for launch. The consequences of this mechanical mastery were profound. Word spread through the Latino community that Miguel could make any car faster than the expensive tuning shops. His garage became a pilgrimage site for serious racers. But it wasn't just about winning races. It was about cultural pride, proving that traditional skills hadn't been made obsolete by technology. The street racing scene in Los Angeles became a laboratory for these techniques. Every weekend, industrial areas in Commerce, Vernon, and Irwindale became impromptu proving grounds. Factory-tuned BMW M3s, Porsche 911s, and Corvette Z06s found themselves losing to 10-year-old Hondas and Nissans that looked like they belonged in a junkyard. In Tran, the numbers were staggering. A proper Miguel-built naturally aspirated B16A Honda could run mid-12s in the quarter mile. That was supercar territory in 2001. For perspective, a Ferrari 360 Modena ran 12.8 seconds. A Porsche 911 Turbo ran 12.5. These were cars costing $150,000 to $200,000, being matched by $10,000 builds using forgotten mechanical knowledge. The cost analysis reveals why this approach was so powerful. A programmable engine management system cost $500 to $2,000. Professional dyno tuning added another $500 to $1,000. Electronic boost controllers, wideband oxygen sensors, and data loggers could push the total to $5,000 just for engine management. Miguel's complete engine optimization, including machine work and assembly, cost about $3,000, but the results were better and more reliable. Engine reliability was perhaps the most impressive aspect. While forum heroes were constantly blowing engines chasing peak numbers, Miguel's builds lasted. His engines would run 150,000 miles of hard use without major issues. The reason was simple. Everything was balanced, clearanced, and optimized to work in harmony. There were no stress concentrations, no harmonic vibrations, no lean spots that created hot spots. And the transmission of this knowledge was entirely oral and practical. Miguel didn't write service manuals or create YouTube videos. He taught by showing. Young mechanics would work in his shop for free just to learn the techniques. They'd watch him feel for valve guide clearance with a valve stem, detecting wear that no measurement tool could find. They'd learn to identify bearing problems by rubbing their fingernail across the surface, feeling imperfections measured in millionths of an inch. This apprenticeship system created a network of skilled mechanics across Southern California. Each had their specialties. Roberto in Pomona was the king of forced induction, able to make turbochargers from two different cars work together in perfect harmony. Carlos in Long Beach could make any automatic transmission shift faster than a dual clutch. Juan in Santa Ana was the suspension wizard who understood that spring rates were only part of the equation. Motion ratios, leverage curves, and installation ratios were equally critical. And the technical innovations these mechanics developed were remarkable. They created anti-reversion chambers in exhaust headers before the aftermarket caught on. They figured out that dimpling intake ports like a golf ball reduced boundary layer separation. They discovered that coating rocker arms with molybdenum disulfide reduced friction more than needle bearings. And on the factory response was initially dismissive. Honda's engineers insisted their designs were optimized using million-dollar flow benches and computer simulations. BMW claimed their motorsport division extracted maximum performance from their engines. But the time slips didn't lie. The Immigrant mechanics cars were consistently faster. And some manufacturers eventually took notice. Honda sent engineers to observe these garages, trying to understand what they were missing. They discovered that mass production necessitated compromises the hand builders didn't have to make. Factory engines had to work with varying fuel quality, survive owner neglect, and meet emission standards. The hot rod builders optimized for one thing, going fast. The cultural impact extended beyond racing. These mechanics became folk heroes in their communities. They proved that immigration didn't mean abandoning your skills. They showed that traditional knowledge had value in the modern world. They demonstrated that craftsmanship could triumph over technology. The racing victories were sweet, but the respect was sweeter. Young guys with computer science degrees and six-figure salaries would bring their cars to these immigrant mechanics, acknowledging that some things couldn't be learned from books or screens. The old-timers had something that couldn't be downloaded or programmed: understanding. The technical principles these mechanics used weren't secrets. They were in old automotive engineering textbooks from the 1960s. Books like Scientific Design of Exhaust and Intake Systems by Philip Smith. The Sports Car Engine by Colin Campbell. These texts explained the physics of internal combustion in detail that modern publications glossed over. The immigrant mechanics had learned these principles not from books, but from experience, arriving at the same conclusions through decades of experimentation. The attention to detail was obsessive. Miguel would degree camshafts, not just to verify timing, but to map the entire lift curve. He'd find that factory cams were often retarded by 2 to 3 degrees from optimal, sacrificing power for emissions. He'd slot the cam gear and advance timing until he found the sweet spot where power peaked without sacrificing idle quality. The valve springs were another area where old-school knowledge dominated. Everyone was installing dual valve springs rated for 600-inch lift, even though their cams only lifted 0.50 inches. Miguel understood that excessive spring pressure increased valve train friction and wore out cams prematurely. He'd use single beehive springs with just enough pressure to prevent float, reducing parasitic losses by 5 horsepower. The modern perspective reveals how prescient these mechanics were. Today's manufacturers have rediscovered many of these techniques. Direct injection systems use bowl-shaped pistons that Miguel was hand-grinding in 2001. Variable valve timing accomplishes what he did with adjustable cam gears. Plasma-transferred wire coatings replicate his hand-applied thermal barriers, and but some techniques remain superior to modern solutions. Hand porting still produces better results than CNC porting because the human eye can adapt to each port's unique characteristics. Mechanical fuel injection, properly tuned, still provides better throttle response than electronic systems with their inherent processing delays. Mechanical limited slip differentials still put power down better than electronic traction control in straight-line acceleration. The data logging revolution actually validated what these mechanics knew intuitively. When affordable data loggers became available around 2005, people could finally see what was happening inside their engines. They discovered that Miguel's engines had perfect air-fuel ratios across the entire RPM range, something tuners with $5,000 ECU setups struggled to achieve. His ignition timing curves matched what professional tuners would later call RARS MBT timing minimum spark advance for best torque. I am the most remarkable validation came from professional racing. When Honda entered the SCCA World Challenge Series, their factory teams were struggling with reliability. They hired several immigrant mechanics as consultants. These mechanics identified problems the engineers had missed: harmonic vibrations at specific RPM ranges, oil starvation under high G forces, heat soak in particular areas. Their solutions were elegantly simple: harmonic dampers on the oil pump gears, modified oil pan baffles, heat shields positioned based on infrared temperature mapping done with their hands. The knowledge transfer eventually went both ways. Younger mechanics who'd learned the old-school techniques began combining them with modern technology. They'd use data loggers to validate traditional tuning methods. They'd use CAD software to design parts but hand-finish them using traditional techniques. They'd program ECUs but verify the results using old-school diagnostic methods. The economic impact was significant. These immigrant mechanics created an entire ecosystem of performance shops that challenged established tuning houses. They proved that effective performance modification didn't require massive investment in technology. A skilled mechanic with basic tools could compete with shops equipped with $100,000 dynos and flow benches. The story of Miguel Santos and his contemporaries represents something larger than automotive modification. It's about the value of practical knowledge in an increasingly theoretical world. It's about the importance of understanding fundamentals rather than just following procedures. It's about the fact that innovation doesn't always mean abandoning the past. Sometimes it means rediscovering it. These mechanics understood that an engine is ultimately a simple device. Suck, squeeze, bang, blow. Everything else is optimization. They approached each engine as a unique puzzle, not a standardized unit to be modified according to a formula. They understood that power came not from individual modifications, but from the harmony of all components working together. And the legacy continues today. While Miguel retired in 2018, his apprentices carry on the tradition. They've adapted to modern engines with direct injection and turbocharging, but the fundamental approach remains the same. Understand the physics, optimize everything, and never trust a computer more than your senses. The philosophical lesson is profound. In our rush to embrace technology, we often abandon proven techniques simply because they're old. We assume that newer must be better, that computers must be smarter than humans. But Miguel and his peers proved that human intuition, developed over decades of experience, could still outsmart silicon chips and sensors. Looking forward, as cars become increasingly computerized and electrified, these mechanical skills might seem obsolete, but the principles remain relevant. Understanding thermal dynamics helps with battery cooling. Knowledge of harmonics applies to electric motor design. The ability to feel and diagnose problems will always have value, even if the problems are different. The story of how immigrant mechanics outsmarted factory cars isn't just about horsepower and quarter-mile times. It's about the preservation and transmission of knowledge. It's about proving that craftsmanship and understanding still matter in an automated world. It's about showing that sometimes the old ways aren't just nostalgic, they're superior. These mechanics didn't just modify cars. They preserved an approach to problem-solving that valued understanding over equipment, intuition over instrumentation, and craftsmanship over convenience. They proved that in the race between traditional knowledge and modern technology, sometimes the smart money is on the old guy with greasy hands and decades of experience. The next time you see a beat-up Honda Civic destroy a modern sports car at a stoplight, remember that it might not be about nitrous or turbos. It might be the result of forgotten knowledge, applied by someone who learned to fix engines before computers told them how. Someone who understands that horsepower isn't bought, it's built, one perfectly polished port at a time. What's your take on this? Have you ever witnessed old-school mechanical knowledge triumph over modern technology? Drop a comment below with your own experiences. And if you enjoyed this deep dive into the forgotten arts of engine building, make sure to subscribe, because we're just getting started exploring the untold stories of automotive innovation.